This video is the second video in a three-part video series discussing the area between two curves. This is designed for a Calculus 1 course and is based on the OpenStax textbook Calculus Volume 1, Section 6.1, Area Between Curves. In the first video, we looked at the area between curves when integrating with respect to x. In the second video, we're going to look again at the area between two curves, but in this case, we're going to integrate with respect to the variable y. Let's take a look now at what's on the screen. Here you'll see that we have two functions, u as a function of y and v as a function of y. These must be continuous functions in order to be able to compute the definite integral. We need a closed interval from c to d, where c and d are considered y variables, not x variables. Note that it is not required to use the letters u and the letter v for your functions. We could simply use f and g again, but instead of being functions of x, they will be functions of y. In this case, we are again trying to find the area between two graphs, but this time we are using the y value c and the y value d to form two horizontal lines, and this will provide a further boundary for the area between the curves. When we think about it, we can again divide the region up into partitions and create rectangles. When we did this with respect to x, our rectangles ran vertically, and that made the differential the narrow end of the rectangle dx. However, when we integrate with respect to y, the rectangles must run horizontally. The narrow end of the rectangle becomes the differential, which is dy. In the picture, let me show you where the dy occurs. The dy is the narrow end right there. This small region there on the end of the rectangle represents the change in the y variable over that rectangle. That is dy, or delta y. We can use the rectangles in a Riemann sum to approximate the area of this region. By taking the limit as the number of rectangles goes to infinity, or as the delta y goes to 0, or the differential gets incredibly small, we can get the precise area of that region. Here is the theorem from the textbook discussing the area between two curves with respect to y. Notice that the functions must be continuous over the closed interval from c to d so that we can compute the definite integral. We will let r this time denote the region that is bounded on the right by u of y and on the left by v of y, and above by the horizontal line y equal d, and below by the horizontal line y equals c. Then we can compute the area of the region by doing the definite integral from c to d of u of y, the rightmost function, minus v of y, the leftmost function. When we integrate with respect to x, it is above minus below. When we integrate with respect to y, it is right minus left. Here is what it looks like if we had expanded the definite integral and written it as the difference of two integrals instead. It is, of course, exactly the same as it was before. We're really finding the area between the curve and the y-axis for each of the different functions and then subtracting the areas. That will give us the area between the two curves. We will again need to find the points of intersection if we're not given the exact closed bounded interval over which to integrate. This will let us determine where these graphs touch or cross so that we can find the values for C and D. Again, the graph will be to the right of the graph to the left. This is the order in which you do the subtraction. We'll use F again for the rightmost and G for the leftmost, but you cannot rely on the names to actually provide the information. You will have to graph them in order to determine which is truly on the right and which is truly on the left, and do they swap places, which does happen often. Also remember that this is giving you the total area between the curves, not net area. That is, that area that you get should be positive because we're simply talking about the amount of space between the curves, not how much is to the right of the y-axis as opposed to the left of the y-axis, or above the x-axis as opposed to below the x-axis. We are instead talking about the absolute value of the area between the two curves. You don't need to worry about it. This simply comes out in the wash in the formula. Let's now take a look at our first example. Example 1 is actually a repetition of example 6 from the first video in this video series, area between curves with respect to x. Let's take a look at what we did before. In the previous video, when we solved this problem, we were looking for the area between the curves y squared equal 4x and g of x equals 2x minus 4. If you look at the rectangles drawn in a vertical orientation, that is, with respect to x, you can see that they change what they touch in the lower and the upper points, from the left to the right. That may mean that will need to divide this into two regions in order to integrate with respect to x. Let's take a look now at what it would look like if we were to flip the orientation and integrate with respect to y. This will make our rectangles run horizontally so that the differential, the short end, is dy. You'll notice that in all cases, all along this closed region, we have the slanted line on the right and the parabola on the left. That makes this a good choice for integration with respect to y. However, I will caution you that if it is not easy to solve the equation for x in terms of y, it may still be simpler to do it instead with respect to x. In other words, if we're switching from dx to dy, I've got to be able to take the original functions and solve them instead of for y, for x instead. Let's solve this problem now. The previous time that we worked this example, we got an answer for the area between the curves of 9. We'll tuck that into our head so that we can check at the end and see if we got the same result. For now, in order to integrate with respect to y, I need to solve for x. That's going to be my first step. I need to rewrite the equations in terms of the variable y, since my differential will be dy. This means that I'll take y squared equal to 4x and rewrite it as x equals 1/4 y squared. I'll take the other function, g of x equal to 2x minus 4, replace function notation with y, and then solve for x. This would give me that 2x is equal to y plus 4, or x is equal to 1/2 of y plus 2, if I divide every term by 2. Now let's take a look again and remind ourselves what the points of intersection would be. We could, of course, set these two equal to each other and find the regions. However, we've already solved this problem once. Let's simply look back at what we did before. If we scroll up, we can find our previous points of intersection were 4, 4, and 1, negative 2. Looking at the graph, this is here at 4, 4, and this is 1, negative 2. Notice also that the back or vertex of the parabola is at 0, 0. Let's go ahead and copy and paste the picture down so that we'll have it to refer to. Moving to the next part, then we'll need to integrate. In this case, we want to go from the rightmost graph, which is the slanted line, but we need to write it in terms of what is when you solve for x, and that would be 1/2 y plus 2. That will be written first. Now we subtract for the formula, but we need to write the equation for the parabola, again, solve for x. That is 1/4 y squared. Once we have the integrand correct, remember that the differential is dy. We need the limits of integration as well, but they must correspond to the differential dy. That means they have to be y values. If we're looking at this region, it is always the slanted line on the right and always the parabola on the left. Therefore, I only need one integral. Big advantage over integrating with respect to x. What is my lowest y value for this closed region? That would be at this point here with y value of -2. My lower limit of integration then is y equal -2. What is the highest y value of this closed region? That would be at the point 4, with y value 4. Now we simply integrate. You can pause the video here since I know you can compute a definite integral. When you're complete, then turn the video back on and check your answer with mine. Let's see how you did. Once you find the antiderivative for each term in the original integrand, you will need to plug in the limits of integration. Be careful with your negative signs. Watch out for double negatives, particularly here where you have the subtraction for doing it at the lower limit of integration and a negative raised to an odd power, which stays negative. That gives you a double negative, resulting in a positive. If you complete this correctly, you will in fact get precisely the same answer, which is 9. Let me shrink the page a bit so that we can compare the length of solving this problem with respect to y versus solving it with respect to x. Integrating this with respect to x took half of this page and this full page, not to mention the graphs. When we do it with respect to y, on the other hand, you'll notice that I really only have part of a page here, another part here, and this small part would definitely fit here. It is a much shorter and simpler process with respect to y, and it only requires one integral compared to doing it with respect to x, which required 2 integrals. Let's look at another example. This is repetition of example 7 from the previous video, area between curves with respect to x. In this particular one, it does say example 6, but I'm pretty sure it is actually example 7. We'll fix that now. When looking at it, we had 2 curves, again a sideways parabola and a slanted line 1/2 x. If you look at this and you look at the rectangles with a vertical orientation, which means that the differential must be dx, you'll see that you change from the far left to the far right which curve is on the lower end. On the left side, it is the lower half of the sideways opening parabola, but on the right side, it is the slanted line. Because of that, you would have to split the area into 2 pieces and compute them separately. If we look at the same curve but change the orientation to a horizontal rectangle, we change the differential from dx to dy. In this case, on the right side of every horizontal rectangle is the slanted line. On the right side of every rectangle is the parabola. Yes, which part of the parabola changes, but it is always parabola on the left and slanted line on the right. That makes this a good candidate to consider doing with respect to y. This does, however, require that you can easily solve that equation for x. Given that we have this expression here, which is already solved for x, it's going to be dead easy. Let's now resolve this problem, but do it with respect to y. We will need our points of intersection, which we found previously to be 6, 3, -2, -1, and for the vertex of the parabola to be at -3, 0. Since it's on the x-axis and the y value there is 0, we get x is -3 on the parabola. Let's now rework this problem. Here's the information we have from our previous working of this problem. The vertex is at -3, 0. The 2 points of intersection are 6, 3 and -2, -1. We know from the graph the slanted line is on the right and the parabola is on the left. In order to rework the problem, but with respect to the variable y, we must take each of these curves and solve them for x. The first equation is already in terms of x. X equals y squared minus 3. The second one is not. It is written now in terms of y equal 1/2 x. However, we can easily rewrite this as x equals 2 times y. Now that I have them both written in terms of the variable y, I can set up the integrals. Remember, you can simply find the points of intersection by setting the two x parts equal to each other and solving. Now that I'm ready, I can set up the integral as follows. I want to have the graph that is on the right first. That's the slanted line, which is x equal to y. I have to use the expression in terms of the y variable 2y. Minus for the formula. Now I must put in the graph that is on the left, which is the parabola. In terms of the y variable, it is y squared minus 3. Notice the parentheses are not optional, since I need to distribute the negative sign. The differential is dy. We need to locate our lowest y value and our upper y value over the closed region. You could take it, of course, off the points of intersection, but let's go back to the graph so that you're sure you understand where it's coming from. If I look at the bottom rectangle, the height there is -1, and the top rectangle will, of course, be at height 3. That goes from -1 to 3. These are the y values on the points of intersection. -1 becomes the lower limit of integration and 3 the upper. Now that we have the integrand complete and the limits of integration in place, pause the video, do the work on your own, and then turn it back on to see if your answer matches mine. Hopefully you were able to complete your integral in record time. If you do, be sure that you did distribute the negative over both terms on the graph that is on the left side. When you plug in the limits of integration, again, be very careful with negatives, particularly those raised to odd powers, since they will maintain the negative sign. Working out the arithmetic, you should end up with 32/3. You'll notice that this took me roughly less than a page, perhaps 2/3. Looking at what was done before, you'll see that again, the answer is 32/3. But in the previous rendition, it took me a full page and almost all of another page. In other words, if you choose the correct variable to integrate with respect to, You can save yourself a lot of time and a lot of aggravation. Let's take a look at another example. Example 3 does not come from the previous video. Instead, we're simply asked to find the area between the curves given by x equals the binomial y minus 2 quantity squared divided by 3 and the function g of x equal to 8 minus x. The fact that they have the first curve solved for x is a good indication that you should at least consider integrating with respect to y instead of x. To truly know if that is a good choice, you need to look at the graph. In order to do that, before we start, let's go ahead and see if we can find the points of intersection. Then we'll look at the graph produced by Desmos and see if we did our work correctly. I think it is better to do the algebra first and use Desmos to confirm that you have in fact found the correct points of intersection. Let's find the points. In order to do that, I need to take this second equation, g of x equal 8 minus x, and write it in terms of x and y. Then I need to solve for x, which would give me x equals 8 minus y. Since I'm looking for points of intersection, those will occur when I have the same point on both curves. Note that I am calling them curves because the first one is probably not a function. If it's not a function, you can call it a curve. If it is a function, you could still call it a curve. If it's a line, which is of course straight, you can still call it a curve. Curves don't have to curve. A straight curve is a line. Curve is simply the generic name for anything you can draw. Let's find the points of intersection by setting the x-coordinates equal to each other. We substitute the binomial y minus 2 quantity squared divided by 3 for x on the left and 8 minus y for the variable x on the right. This will give us something that is quadratic in y. In order to solve this, we will want to go ahead and multiply out the binomial that is on the left, and then we will want to perhaps move the 3. Actually, I think I'd rather move the 3 first. I'm going to rewrite this as y minus 2 quantity squared, and distributing the 3 on both sides will give me 24 minus 3y. That avoids the fraction and makes it easier to solve. The left becomes y squared minus 4y plus 4 equal to 24 minus 3y. Make sure that you move all the terms to the same side of the equation so that you can get the quadratic equal to 0. In this case, I'm going to move everything to the left side where I have a positive y squared term. This gives me y squared minus y minus 20 equals 0. This can, of course, be factored. If I want to factor this, this would give me y minus 5 as a binomial factor times another binomial factor, y plus 4. This gives me two possible solutions. This gives me y equal 5 or y equal negative 4. I can use either equation to find the x-coordinates. Remember, these are points of intersection. They're on both. I'm going to use the equation x equal 8 minus y since it's simpler. X equal 8 minus y, if I use the y value of 5 and plug it into this equation, 8 minus 5 would give me 3. That's the ordered pair 3, 5. Now let's take the y value negative 4 and replace the y. Since this involves negatives, I'm going to be a little more careful. This is 8 minus from the formula, but the y value itself is negative. That's 8 minus a negative 4, which gives me 12. Now this would be the point 12, -4. Let's take a look now at the graph produced by Desmos and see how we did. If we scroll down, we can see then that the graph is down here. Hopefully I can pull the thing up. And you can see that I have got my 2 points of intersection. This looks to be at 12, -4. Is that what I got up here? Yes, it is. The other point of intersection appears to be at right 3, up 5, which would be 3, 5. That is the other point that I found. Now I am ready to set up the integral to integrate with respect to y. Notice that for this region, if I were to draw my rectangles moving from the top to the bottom between the left and the right side, every rectangle has the slanted line on the right and the parabola on the left. The horizontally oriented rectangles have the differential dy. Notice that if I were to reverse the orientation and make the rectangles vertical, what was above and below would change as I moved across this region. That makes integrating this with respect to y the logical choice. You'll see here that I need to go from a low y value of -4 to a high y value of 5. It is the slanted line always on the right and the parabola always on the left. Here are the equations that we have again. And again, I need to go from -4 to 5. Setting up the integral then, I will have -4 to 5 for my limits of integration. Remember that you need to use the rightmost line, which is the line, and you will subtract from that the leftmost curve, which is our parabola. This will give me 8 minus y, again solve for x so that it is written in terms of the variable y, minus, now I put in the parabola. You'll notice that I moved the 1/3 from the denominator out to the front just to make it easier to integrate. Now that I have this here, don't forget that the differential is dy. Now you do have a choice. You could multiply out the binomial, or you can do a u substitution and integrate without multiplying it out. It is purely a matter of choice, which I will leave up to you. Pause the video here, compute the definite integral, then turn the video back on, and let's check our answers. How did you do in your integration? I chose to stick with what was written and to do a u substitution. This required a change in the limits of integration, or you could have kept the y values but had to substitute back into y minus 2 instead of leaving it in terms of u. When I was done, I ended up with the answer 27 square units for the area between the curves. Let's now look at another example. Example 4 is our final example for this video. It is also probably the most difficult of the ones that we are looking at. If we are looking at this particular one, we are to find the area between the curves given by x equal 2 times sine squared of y, and the curve g of x equal to x squared. In order to find where these cross, you would need to be able to solve for x in both of them, or y in both, or to use substitution. In this case, it is already set up so that you could do a substitution. If I were to do substitution, I would need to solve the second equation and write it as y equals x squared, and replace the x with what we have in the first curve, which is that x is 2 times the sine squared of y, and then square it. Unfortunately, if I do this, I end up with y both inside the trig function and outside the trig function. It will be impossible to solve this for y. In this particular problem, it is actually simpler to graph it and look at the graph first, and then to go from there, rather than try to solve it algebraically. It cannot be done purely algebraically. You'll have to use trig as well, and it is quite complicated trig and algebra at that. In that sense, then, what you might do instead is try to consider doing the substitution in a different direction. Unfortunately, that would simply give you x as both the argument to sine and x on the outside. Same problem, different variable. In order to solve this one, what we will do instead is simply look at the graph produced by Desmos and go from there. If I were to give you one on an exam, I would probably give you the picture so that you could go from the picture to determine the correct integral. I would not give you just the equations and expect you to know what to do. Let's look at the graph now. As you can see, this is a complicated graph. It's not simple. What's happening in this curve right here is that we have the sine function running, yeah, you've got it, vertically, not horizontally like we're used to. This is because we've swapped the variables of x and y in its representation. You'll notice that when I put it into Desmos, instead of writing sine squared of y, I wrote in parentheses sine of y quantity squared. It should still work if you write sine squared of y. The only time I'm extra careful is when the argument to the trig function is more than a simple variable y or x. In those cases, I tend to use parentheses because occasionally there are glitches in the code and you could possibly get the wrong curve. You'll see here in black the simple parabola. Now, we do have some closed regions, but most of them are wide open. Do not mistake the y-axis and the x-axis for boundary lines. You can ignore them completely. They are not cutting off the region. The only thing that cuts off the region is the black parabola that you see here and the purple vertically oriented sine function that you see here. I do have a small closed region here and another region here. And while it looks like this might be closed, it also looks like there might be a narrow gap there. In order to determine it, we should blow up the graph and take a closer look. Here's a closer look at the region that we're concerned about. You'll see that there is in fact a gap. This will not hold water. If you pour it in here, that water's going to come gushing out that gap. It's not going to turn into a swimming pool. On the other hand, this region here will be a swimming pool, as will this tiny little region here. Let me shade in the regions so that you can see exactly where we've got space that is being enclosed completely by the two curves. Here's the first one in that tiny little region there. Notice that we have in this section the parabola on the right and the sine function on the left. Again, this is for horizontally oriented rectangles. This region, however, could just as easily be done with respect to x, since I have the sine always on top and the parabola always on bottom. In this region, it makes no difference whether I integrate with respect to x or y, provided I can solve the equation for both variables. That is where I hit a wall on this one in integrating with respect to x. In order to integrate with respect to x, I would need to solve this equation, you got it, for y, and that would involve the arcsine function, which I would like to avoid. Therefore, I will not integrate with respect to x, but will instead integrate with respect to y. What about this other region that we're looking at? Let's color that one red so that we can compare it to the first one. That would be this region here, which of course is also closed and bounded and will hold water. When I'm looking at this region, would it be the same going with respect to x as it is with respect to y? Definitely not. On the right, I always have the sign-related function. On the left is always the parabola. However, if I were to orient the rectangles vertically, which gives me the differential dx, I have first the parabola on top the parabola on top and the sign-related function on bottom. And on the far right, I have only the sign-related function on both the upper part and the lower part. This would be a nightmare to have to integrate with respect to x. Instead, we should integrate both regions with respect to y. We will need our points of intersection in order to be able to compute them. You can see that they must both intersect at the origin, which is 0, 0. That will give us that point there. How can we find these 2 points, which are here? In order to find those 2 points, we need to be able to figure out when the two coincide. Let's see if we can determine that. For the purposes of this problem, in order to find where the points of intersection are, we'll refer back to the graph and we'll simply click on the graph. When I click on one of the points of intersection, the others will also pop up. I can then click on all 3 at the same time. This will give me the points 0, 0, 0.84, 0.7048, and 1.456, 2.12, roughly. Let's copy and paste this over so that we can see where this would be when we do the integration. Let's now set up our integrals based on the information that we can see here. We'll simply round instead of to 4 decimal places, we will round to 2. This will give me instead the integral from 0 to the next y value, which is 0.7048, rounded. I suppose let's go to 3. We'll make it 0.705. That should give us a relatively accurate answer. Now I need to know in this region here which graph is always on the right. That's my parabola. Now again, since my differential is dy, it must be solved instead for x. If I'm going to solve this for x, remember that my parabola was originally y equals x squared. Solving for x, I get plus or minus the square root of y. Looking at the parabola, you can see that this part here is the right half of the upward opening parabola. That is the positive square root of y. That makes my first one here in the integrand become the square root of y. Minus for the formula, now we need the graph that is on the left side of that first closed region. That is this equation here, which is already solved for x. Thus, I can simply substitute 2 sine squared of y, all with respect to y. Now I need my second integral for the second closed region. This will go from 0.705 up to 120 actually, 2.12. This would be the integral again from 0.705 to 2.120 if we rounded to the third decimal place. Now, in this region, it is instead that sign-related function on the right, and it is instead the parabola that's on the left. We will then reverse the order. This will give me the expression 2 sine squared y as the first part here, and the second part will be the square root of y because it is, again, the right half of the upward opening parabola. And that will give me the square root of y, dy. Now that we have the definite integrals set up, go ahead and turn the video off, compute the definite integrals, then turn it back on to check your answer. I have to admit, if either one of us made it to the end of these ugly integrals without an arithmetic error, it will be a miracle. However, you can compare what you have to mine, and maybe between yours and mine, you can work out all of the errors. I did round off in all places to 3 decimal places, though technically you should not round until the final answer. You'll see that I did need to do a u substitution when I got the cosine of 2y. Notice that that came from making a trig substitution for sine squared of y, since we currently don't have a way to integrate that in Calculus 1. Instead, you replace it with the double angle formula that sine squared is equivalent to 1/2 times the quantity 1 minus cosine of 2y. Be very careful with your signs, and as you work your way through, you'll end up with a couple of integrals that have cosine of 2y in them. Keep track of all of the different limits of integration. You'll notice in the next line, when I did do the u substitution, I did not replace the variables, but kept them as their y values. I thought this would be simpler than having to reverse and go to u, but perhaps I was mistaken and you chose to switch the limits of integration and found it to be simpler. When I was done computing all of this and rounding off my numbers, I did get a rather startling result. I was shocked to get precisely 7/8 despite my rounding. I am not at all confident that 7/8 is the true value, but I do know that the area must be in fact quite close to 7/8, and it is possible that it is precise, but highly unlikely due to the rounding. I hope that you have learned something about how to integrate with respect to y when finding the area between two curves. In the final video in this series, we will instead be looking at curves for which we don't know which way to go to determine which way to go. Integrate with respect to x or integrate with respect to y. This is the end of this video.